So there's a number of kind of classic application problems and formulas that start from separable differential equations. And we're familiar with a lot of these already in even our algebra classes. Real quick example is the natural growth function that we know quite well, right? Y of t equals some constant e to the kt, or sorry, yeah, we'll put it like that. Change our constant here. We'll call it y sub 0. Right? So when we have exponential growth, that's the equation we use. When we have exponential decay, we use that same equation, but with a negative k, which is the growth rate. And this equation starts from a differential equation, and it starts from the differential equation. We'll use slightly different notation. Dx dt equals k times x. So we're saying the change in if x is the population size, whether it's the population of a city, a country, or the population of our bank account, money. X is the size, the population size, and then dx dt is the how the population is growing. This equation is saying that the population is growing at a rate, the population growth is proportional to the population. So real simply, if we've got a larger population, then the growth rate will be bigger as well, and same for smaller. But that's the differential equation. This is a separable differential equation, right? We can solve this by separating the x's and the t's. We'll just put it up here. So we end up with dx over x equals k times dt. And if we go through the procedure of solving this for x, it looks like this. We get ln of x, and we're going to normally that'd be absolute value of x, right? But again, x represents the population size, so x is really, we're only interested in x being positive. A positive population. Negative populations don't make any sense. Remember, this is population, and this is kt plus our constant. So we don't have to worry about the absolute value, and that's the equation. We exponentiate both sides, leading to x equals e to the kt plus c, or e to the kt e to the c, or like we've talked about before, c sub 1 e to the kt. And sometimes I just kind of get lazy and just call this c again, even though it's right, it's just a constant. That's the point. But there's our equation, right? There's our exponential growth equation. Okay, so we have several of those situations that come from these differential equations. Of course, you've got the differential equation that leads to exponential growth and exponential decay. You've also got, as we've already mentioned, the Newton's law of cooling. Which comes from this differential equation, which again is separable. The capital T is the temperature function, and of course little t is time. Dt equals some constant times A, where A is the constant temperature, ambient temperature, A minus T. And there it is. There's Newton's law of cooling. And we can separate that because we can write this side as a function of capital T times a function of t. Not a big difficult thing to solve. In fact, it's even easier than that. We just simply integrate both sides because we don't have little t on that right hand side. But that's another classic differential equation that leads to the Newton's law of cooling formula. Another one called Torricelli's law, which has to do with a water tank that is draining, that has a hole in the bottom of it, and we know the area of the hole, and it'll tell us the change in the volume. It'll allow us to find a formula for the volume of the tank, but you'll find that in the textbook, right? And so all of these problems, all of these differential equations lead to these formulas that we can use to answer questions. And if you've done any algebra, you've seen lots of exponential growth and decay problems. Let's just look at a real simple one here and see how it works. So here's kind of an interesting problem. If you want to follow along, this is problem number 39 in the book, but I'll describe it a little bit. We're talking about anesthetizing dogs, and so that we can perform surgery on them. We're going to use sodium phenobarbital, and the dog is considered to be anesthetized when the bloodstream contains at least 45 milligrams of the drug per kilogram of the dog's body. Okay, so we need a certain amount of drug in the bloodstream for the dog to be asleep, basically. Suppose also that the drug is eliminated exponentially, okay, from the dog's bloodstream with a half-life. The half-life is 5 hours, right? So we know what a half-life is. After 5 hours, there's half as much as there was at the beginning of the 5-hour stopwatch. So the question is, what single dose should we give a dog in order to put them to sleep for 1 hour? And this dog weighs 50 pounds. So how much for a 50, I guess kilograms I should say, 50 kilogram dog for 1 hour? So in other words, we need there to be at least 45 milligrams per kilogram in the dog for 1 hour. Okay, so if we translated that, let's see, 50 times the 45, that's going to give us the amount we've got to have in order to keep the dog asleep. Okay, so we've got to have at least 2250 milligrams of the drug in the bloodstream. Okay, so being an exponential decay problem, let's just let y equal the amount. We know what the formula looks like, right? Some constant, we're going to put y sub 0 times e to the kt. Now we know k had better end up negative. We don't have to put a negative there if we do our math correctly. We'll just use kt. So this would be the model that describes how much drug is in the dog's bloodstream. We need to figure out two things. Those two things. You got to figure out the constant k of decay, and you've got to figure out the y sub 0. Now y sub 0, so the reason we write y sub 0 most often is because that is the initial amount. Okay, that's how much we start with at time 0. And in fact, that's the question. How much do we need to give the dog in order for them to be asleep? So we don't know the answer to that question right now, and we can't figure it out. However, we can figure out what k is, right? And so we need, in order to figure out what k is, we're going to use this half-life idea. So I don't know how much I started with at time 0. But after 5 hours, if I plug 5 in there, I better end up with half of what I started with. Okay? And this is this is a typical way to use half-life. But this will allow us to solve for k. And of course, if we look at this, we see, oh, we can divide both sides by y sub 0. So we end up with just this right there. We take the natural log of both sides. If you remember your natural log, so we'll squeeze that in there. We take the natural log of both sides, so the natural log of 1/2 equals natural log of e to the 5k is just 5k. So this tells me k is going to equal the natural log of 1/2 divided by 5. So let's throw that into our calculator real quick and see what k is. And so if our calculator has done everything correct, we should get k is negative 0.13. We'll round to 3 decimals, 139. Okay, so up to this point, we've got this much of our model figured out. And like we said, we ended up with a negative k. Okay, so now the task, before we can come up with a model that we can just use to figure out how much drug is in the dog's bloodstream, we need to figure out what y sub 0 is. And so that's our next task. So the way we're going to do this is we don't know how much we start with, but we know how much we need after 1 hour. Okay, and that is this. Remember, we need at least 2,250 milligrams to still be in the dog's bloodstream for him to be asleep after 1 hour. So that means, using our little formula, let's do the right hand side. Don't know what y sub 0 is, but if I plug in 1 here, I better get 2250 out. And this will tell me how much I need to start with. So 2250 divide by e to the negative 0.139, which is the same as multiplying by e to the positive 0.139. Don't give me all that. Right? And so if we throw that into our calculator, we're going to find out y sub 0, which is how much we should start with, which is how much we should give the dog. So there it is, 2,585.529. If we start with that much, then in an hour we will have 2,250. And then of course we're going to round a little bit, just because we need to start with more than that to make sure that we have more than our minimum amount. And so a lot of these problems will look like that. Notice we didn't start with the differential equation in both exponential and exponential growth and decay. You can start often with just the formula, the exponential growth and decay formula, but with the other ones you'll probably have to start with the differential equation and solve it to see what the formula is.